Good morning, everyone. My name is Susana E. Devota. My topic for this morning is about finite field. Before I start, I have here my objectives. At the end of the discussion, the mathematics students should be able to define finite field and explain finite field. Finite field or a Galois field. In mathematics, a finite field or a Galois field is a field that contains a finite numbers of elements. As with any field, a finite field is a set on which the operation of multiplication, addition, subtraction, and division are defined and satisfy certain basic rules. Another definition of a finite field is a finite set F with two binary operation, addition and multiplication that satisfy the following. Number 1, F plus 0 is an abelian group with 0 as the identity. Second, F minus 0 multiplication operation 1 is an abelian group with 1 as the identity, and the multiplication inverse is denoted by a raised to the power negative 1 is the element of F. Number 3, multiplication can be distributed over addition. Example, for any ABC is an element of F, then A times B plus C is equal to B plus C times A is equal to A times B plus A times C. The finite field is denoted by F, addition operation, and a multiplication operation. Classification of finite field. A Galois field with Q that satisfy the property of a finite field exists if and only if Q is equal to P raised to the power of M, where P is a prime number and M is the integer. Example, GF 2 with the elements 0 using modulo 2, addition and a normal multiplication, using our addition and our normal multiplication of a natural number. Note that modulo 2 addition, a plus b is equal to a plus b modulo 2 modulo 2. This is our addition table. So, 0, if we are going to add 0 plus 0 is equal to 0, 0 plus 1 is equal to 1, 1 plus 0 is equal to 1. 1 plus 1 is equal to 2 using our modulo 2. This is equal to 0. And this is also our multiplication table. If we have to multiply 0 plus 0, it is equal to 0. 0 plus 0 times 1 is equal to 0. 1 times 0 is equal to 0. 1 times 1 is equal to 1. Next is the subfield of a finite field. And Theorem 22.3. For each divisor m of n, g, f, p raised to the power of n has a unique subfield of order p raised to the power of m raised to the power of m. Moreover, these are the only subfields of gf p raised to the power of n. Example, if you have a field with 5 raised to the power 12 elements, what is the total number of subfield? Let FQ be the finite field with Q is equal to P raised to the power of n elements. Then every subfield of FQ has order P raised to the power of n, where m is a positive divisor of n. Conversely, if m is a divisor of n, so m divide n, then there exists only one subfield of if q with p raised to the power of m elements. Example, 5 raised to the power 12. The number of elements in its subfield is m over 12. It is stated that m divides n. So, 1, the possible divisor of 12 are 1 divide 12, 2 divide 12, 3 divide 12, 4 divide 12, 6 divide 12, and 12 divide 12. So this is now the subfield of 5 raised to the power 12. So the subfield of 5 raised to the power 12 are 5, such that 5 raised to the power of 1, 5 raised to the power of 2, 5 raised to the power of 3, 5 raised to the power of 4, 5 raised to the power of 6. 12 is not included because 12 is equal to the elements of 5 over 12. Another example, f having 2 raised to the power of 6 elements. So the answer are 2 raised to the power of 1, 2 raised to the power of 2, 2 raised to the power of 3, and 2 raised to the power of 6. Another example, example number 3, f is equal to 3 raised to the power of 8. 8. How many proper subfield does this field has? Subfield having elements of 3 raised to the power of 1, 3 raised to the power of 2, and 3 raised to the power of 4. So these are the subfield of 3 raised to the power of 8, since the divisor of 8 is 1, 2, and 4. Okay, for the evaluation, this is good for 20 points. In your own words, what is a finite field? Second, let F be a field of order 4096. Find the number of proper subfields of F. Gate 22 MA. That's all. Thank you and God bless.